Welcome to the Explainer. We're about to embark on a journey that absolutely shatters our everyday understanding of reality. So forget that static, peaceful tapestry of the night sky you're used to seeing. Today, we're diving straight into an extreme, dynamic arena that harbors the cosmos' most unfathomably powerful entities. We're going to visually dissect the universe's ultimate apex predators, black holes and pulsars, and decode the mysterious fabric of space-time that they violently manipulate. So, what actually happens when the laws of physics are pushed to their absolute limits? That's the question keeping astrophysicists awake at night, right? What happens when the comfort and classical mechanics that govern our own solar system are stretched, warped, and pushed right to their absolute breaking points? To really understand these cosmic predators, we've got to abandon our earthly intuition and prepare for extreme mass, blinding radiation, and gravity so intense it literally breaks light. Section 1, the fabric of spacetime. Okay, before we meet the monsters themselves, we really need to understand the fundamental architecture of the environment they hunt in. Look at this glowing grid-like funnel. It's visualizing something that is completely invisible to the human eye. The universe isn't just an empty void. It actually relies on an underlying architectural grid. And when a massive object exists within it, that grid sags. It stretches into a deep funnel, creating a gravitational well. The denser the object, the more extreme this deformation becomes, forcing surrounding matter to violently accelerate toward the center. This bending, this violent downward stretch, well, that's exactly what we experience as gravity. And it's crucial to realize that space and time are not distinct things. They're inextricably woven together into a single, four-dimensional, continuous fabric, which we call spacetime. You, me, the Earth, the stars, we all exist within this fabric. The defining superpower of our cosmic monsters is their sheer ability to grab this fabric and twist it entirely beyond recognition. Grasping this continuous 4D grid is really the key to understanding their dominance. Section 2, Pulsars, Rapid Magnetic Lighthouses. All right, now that we know what the cosmic stage looks like, let's meet our first heavyweight contender, born right from the violent deaths of massive stars. Notice the sheer, unadulterated energy of those brilliant blue jets blasting out into the void. When a massive star goes supernova, its core collapses down into a hyperdense neutron star. If that core spins rapidly and emits blinding beams of electromagnetic radiation from its poles, boom, it becomes a pulsar. As it rotates, these highly focused relativistic beams sweep across space, exactly like a cosmic lighthouse. When that beam sweeps across Earth, our telescopes catch a flash, a pulse of light. But it's not just a clean, simple beam. Notice the chaotic, twisting loops surrounding the core here. This is an impossibly intense magnetosphere. We're talking trillions of times stronger than Earth's. These twisting magnetic fields act as violent engines. They literally rip charged particles right off the stellar crust, accelerate them to near light speed, and blast them out in a terrifying, hyperactive storm. And they do all of this incredibly fast. 716. I really want you to let that number sink in for a second. Astronomers have discovered a pulsar that spins on its axis 716 times in a second. Imagine an object heavier than our entire sun, crushed down to a sphere roughly the size of Manhattan, spinning 716 times before you can even blink. The centrifugal forces at the equator of this star are almost unimaginable, pushing the very boundaries of what atomic matter can withstand without completely flying apart. So we have pulsars on one side, frantic, blazing, hyperactive engines defined by rapid spin and extreme magnetism. But the universe is full of contrasts, isn't it? If a pulsar is a hyperactive storm, our next subject is the crushing, inescapable silence. We're moving from objects that blast light across the galaxy to objects that swallow it forever. Let's pivot to the ultimate apex predator of the cosmos. Section 3, Black Holes, Gravity's Abyss. We're now entering the domain where the collapse is absolute. When a star is so incredibly massive that not even the hyperdense matter of a neutron star can stop its collapse, it just keeps shrinking. It caves in on itself entirely, punching a bottomless hole in that fabric of space-time we talked about earlier. And when matter gets too close, it forms this violently hot, fiery ring, the accretion disk. The black hole's gravity forces surrounding gas, dust, and torn-apart stars to spiral inwards at relativistic speeds. The sheer friction of the superheated plasma rubbing together heats it to millions of degrees. It creates this spectacular, violent feeding frenzy right on the edge of oblivion. But then there's a boundary, a threshold where the glow stops entirely, and total darkness begins. This is called the event horizon. Think of the event horizon as the ultimate point of no return. Once anything, a speck of dust, an astronaut, even a photon of light, crosses this invisible spherical boundary, it's permanently lost from the observable universe. That downward funnel of space-time we saw earlier, it becomes infinitely steep here. The escape velocity required to leave is faster than the speed of light. And since absolutely nothing in the universe can travel faster than light, nothing can escape. Unlike the fiery orange disk we were just looking at, this cold, ghostly view proves just how bizarre a black hole's grip on space-time really is. Look closely. The disk appears to arch over the top and dip below the bottom simultaneously. This is gravitational lensing in action. The gravity is so intensely warped here that it literally bends the light traveling from the back of the disk over the top, allowing us to see it from the front. It's using its massive gravity as a cosmic funhouse mirror, completely distorting our view of reality. Okay, to lock this in for our understanding, let's quickly review the anatomy of this abyss. At the very center lies the singularity, a point of infinite density where all the mass is crushed into practically zero volume, and honestly, our current math completely breaks down. Surrounding that is the event horizon, the inescapable point of no return. Orbiting the horizon is the fiercely glowing, superheated accretion disk, and the whole shebang exists within a pocket of severely warped, fundamentally distorted spacetime. Those are the physical components of the most terrifying objects known to science. Section 4. Embracing the cosmic unknown. We've spent this explainer diving into the absolute extremes, from gravitational grids to spinning lighthouses to devouring maws. But let's zoom back out for a moment. What does the existence of these monsters actually tell us about our universe? I absolutely love this quote from astrophysicist Neil deGrasse Tyson. "The universe is under no obligation to make sense to you." It perfectly captures everything we've looked at today. We can build models, we can map out accretion disks, measure a pulsar spinning 716 times a second, and visualize the bending of light. But at the end of the day, these cosmic predators fundamentally challenge human intuition. They prove the universe is far stranger, far more violent, and honestly, far more awe-inspiring than anything we deal with in our daily lives. Which leaves us with this final, thrilling thought. If our cosmos already contains spinning stars that act like particle accelerators and literal holes in space that swallow light itself, what mysteries still lie hidden beyond our current scientific horizons? What other cosmic monsters are out there just lurking in the dark, waiting for our telescopes to finally catch a glimpse of them? The next time you look up at that seemingly quiet, peaceful night sky, I hope you remember the beautiful, chaotic, and terrifying engines humming away in the deep. Keep questioning, keep learning, and I'll catch you in the next explainer.